video to upload, and sorry about that. And I did not turn it on. Okay. Now for this, have you determined the areas under the curves, leftmost point, rightmost point, and midpoint?
I tried it and got kind of confused.
Okay, on which one?
I was confused. I didn't know if I had to go from 0 to 1. I didn't know if I had to split that into 4 and then 1 to 2 into 4.
No, the whole interval. You are calculating the area under a certain curve on this interval. That's what you split. Because if you use between 0 and 1 and 1 to 2 and so on and so forth, then you'll have way more subintervals than the problem was asking you to use. I'm not saying it's not good. I'm saying it's excellent because you're going to get a better approximation. But that's not what the problem is asking you. So if it says approximate using 4 subintervals, that's all you have. If it says 8, that's all you have. So I wanted to show you.
And I was wondering, how would we be able to use the summation notation to, how can we plug summation notation into that word problem?
For the area?
Yeah.
The sum of delta x times f of xi.
Oh.
Base times height plus base times height plus base times height. That's a summation notation, right? But I want to show you why, one other reason why I treasure my 86. And you know I don't take credit when credit is not due to me. And we had a math professor who retired, I want to say maybe at least 12 years ago. Awesome person. And he created, but not for 84, and not for 83, and not for any other calculator, just for 86, because he loved 86 as much as I do. He created tons of programs. I did transfer them to everyone who has an 86, but I couldn't transfer them to anyone who has anything else. So in this situation, I'm looking for, I passed it, that's why I'm starting again. Here it is. He created a Riemann Sum program. So I recall it from the list of programs, and I press enter, and this is his name, Gary Van Velser. He created this program for everything, for Newton's method, for just everything. I have an app, in other words. He didn't even know he was creating apps. Okay, so x squared plus 4. So x squared, I was just saying that I have to go back and change, but I didn't use this calculator for sequence. X squared plus 4 is the function. So this program gives a Riemann sum for f of x on the interval a1 comma b1 using n1 rectangles. So I can put in the interval, and I can put in the number of rectangles. And not only did I get the approximation left, right, midpoint, but he also calculates the error. This program calculates the error between whatever I'm determining and the exact area. So it's an awesome calculator. That's because he worked on it so much. So A1, so we have 0. B1, so we have 2. And how many subintervals? Let's say 4. Now it's even asking me left, right, midpoint. So let's go ahead with the right. The Riemann sum with the right is 11.75. So now choose F1 for the left endpoint, and it will give it to us. F2 for the right, F3 for the midpoint, F4 to quit. So now if I want to determine, it says for the actual value and error, F1, for more, F2. I'm just going to do the error. So we obtained, so the actual value is 10.66666667, and the error is 1.08. And it can do this, the program can do this for any number of subintervals, for any interval, for absolutely everything. So do we still need to illustrate one of these problems by hand? Leftmost point, rightmost point, midpoint.
Are you doing midpoint?
Yes,
Midpoint
which,
just
yes,
take left and right divided by 2?
yes, but that's for the x value. You cannot do it for the y values. So the leftmost point means that you are choosing the height at the left point of the subinterval. The rightmost point means that you are using the height with the function at the rightmost point. The midpoint means that you are determining the midpoint of the subinterval, and that's where your height is, f of that value. So which function and which problem? Yeah, but which function?
The x squared plus 4.
Okay, so we want to look at x squared plus 4. So let's start. And today I think it's, thank you. Very good. So we want f of x, which is x squared plus 4. We want how many subintervals? I mean, let's do it with a little with 4 only because of the time. But if you do it, if you know how to do it with 4, you should have no difficulties with 8, 16. Is that okay? So the interval is 0, 2, and we want midpoint. So when I graph this function, so this is 1 and this is 2, and x squared plus 4, for 1, 1 plus 4 is 5. Again, I didn't plan ahead, of course. 1, 2, 3, 4, 5. And then I have 2, which is 4 plus 4 is 8. 6, 7, 8. That's not too bad. So at 0 is 4. At 1 is 5. And at 2 is 8. So this is the graph. I'm asked to use 4 subintervals. So these are the 4 subintervals. So obviously this is 0.5 and this is 1.5. So this, and this are the midpoint. So this will be the height, this will be the height, this will be the height, and this will be the height. Therefore, this will be the interval, or the area, I should say. This will be the interval and the area. This will be the height, in other words, this will be the area. And the last one, this will be the height, and this is the area. So I will say the area with a midpoint is approximately the sum from I equals 1 through 4 from delta x times f of xi. I will explain the xi. This is the time we're going to do this today. Okay? So delta x does not depend on where I am, right? Because delta x is always 0.5. How do I know? Delta x is b minus a over 4 subintervals. B minus a divided by the number of subintervals. Like Gary had it in the program, b minus a divided by n. So 2 minus 0 divided by 4, 2 over 4 is 1/2. So delta x does not change. Now you can say, if n goes to infinity, does it matter if one interval is bigger than the other? It doesn't, because n goes to infinity will fill in everything. But we look at the situation in which all subintervals have the same width. Okay, so I can take like a constant. We know this from last time. I can take it, it's a constant, I can take it outside. So this is 1/2. So this is the sum from I equals 1 through 4. I only have 4 subintervals. And f of xi. What is xi? When I is 1, f of xi is this value from this point till this point. When I is 2, f of xi is this value between this point and this point. When I is 3, on the third subinterval, this is f of xi. And when I is 4, I'm here, and this will be the height that will be represented by f of xi. So 1/2 f of 0.25 plus f of, so when I is 1, I have f of 0.25. Here I am right in the middle between 0.5 and 1, so this must be 0.75 plus. Here I'm right in between 1 and 1.5, so this will be f of 1.25 plus. Between 1.5 and 2, this must be f of 1.75. And I promised last time I did it quickly, and I want to do this one more time with you. You may be able to use it. I'm hoping you will. So I can use, in order to, especially when I have 8, 16, or 100, right? We're not going to get to that. There's no need for that. But here's how I recommend we do this. First of all, I have to go back to mode. I have to change it back to a function. And then I go to second and list. No, sorry, just list, just that. And I want to edit. My first list will consist of these 4 values of x. 0.25, enter. 0.75, enter. 1.25, enter. And 1.75, and enter. Now I go to the top of list L2. The top, the very top. And I want the calculator to calculate taking each x, squaring it, because that's our function, plus 4. So the very top in L2, that's what I'm going to put, but my x's are in list L1. So second list L1 squared plus 4. So when I hit enter, I will get in list L2 everything already the function value for each point, because that's how I created L2. L2 will take every entry in L1, square it, and add 4 to it. And when I press enter, this is what I get. What am I after is the sum of these numbers. Of course, I can use the sum of the sequence instead of this. That's another option. But now I want the calculator to give me the sum of L2. Here's how I do it. Second and quit. Go to stats and go to calc and choose the first one. One variable statistics. Make sure you have which list. Which list do I want to sum up? L2. Second L2. And just press and calculate. And you get the sum. Look at it. The sum of all those entries in list L2, the sum of all entries in list L2 is 21.25. So then I go back, and this is 0.5 times 21.25. I can also incorporate that 1/2 if I wanted to. So how do I do that to incorporate 1/2? So I go back to my list L2. Sorry. I go back to my list L2. And now I want to incorporate this 1/2, so I don't have to do that by hand or multiply by 0.5. So I'm going to say this, 0.5, because I have a 0.5 in front. Parentheses, list L1 squared plus 4, close the parenthesis. So now that delta x is multiplied by each and every entry. So I press enter. The numbers will change. And now go back to second and quit. And redo the one variable stats. On list L2, scroll down to calculate. And it will give us the multiplied of 21.25 times 0.5, which is 10.625. The other option is with the sum of the sequence that we just learned today. So the answer, one more time, is 10.625. And this is the area found under the graph of x squared plus 4 between 0 and 2, using having a huge error, right? Because we only used 4 subintervals. Still big, possibly, because we only, as I said, we only used 4. Now, we can determine this using the sum of the sequence and put 1/2 in it. And we should get the same thing. And again, I cannot show it with a calculator. So let's do that. So I'm going to go to I'm just going to copy all this. And our function is 0.5. And in parentheses, n squared plus 4, close the parenthesis, comma, n, comma, from 1, comma, through 4, close the parenthesis, close the parenthesis. When I press enter, I have to get 10.625. If I don't, I messed up something somewhere. Okay? I did mess up something somewhere. Okay, delta x is 0.5, n squared plus 4, close, n from 1 to 4. Sum of the sequence. I had 0.5, n squared plus 4. Unfortunately, this does not calculate with the midpoint. Sorry about that. We can't do it because it does not calculate using the midpoint. It does not give me the option of using the midpoint. So that's why this doesn't work. Yes?
You can use the midpoint doing it that way, can't you? If your interval would stay the same, but your start and your finish. So like as in this case.
Yes, but it will not jump. It will not jump from 0.25 to 0.75 to 1.25 to 1.75. It only plugs in integers. It only plugs in 1, 2, 3, 4.
Yeah, but so instead of using 1 and 4, if you wanted to do the midpoint, couldn't you would start at 0.25 and go to 1.75 and then go up, and then there's a last parameter by what do you want to increase is instead of 1.
If I choose the increment, yes, yeah. Yes, that is possible. So 0.25 to 1.75, and I change the increment as the increment between. It has to be 0.5.
Yeah.
Close. Yes, 10.625. Yes, if I change the increment. So I never asked you or told you to put the increment because we only used 1, but you can change that in the increment into 0.5. Yeah, we never talked about the increment because I didn't think of doing this with the graphing calculator. Excellent, thank you, Tony.
Sure.
appreciated. Very good. Is this clear now, what we have to do and how do we determine the approximations, the areas? Ian, is this okay?
Yes.
Okay. Very good. So let's continue now with 5.2. If I find it here. Yes, I did find it. Any questions, by the way, on 5.1 or 4.9? Any questions on? Yes, please. Tony, go ahead.
There was a question from 4.9's homework. I was wondering if we could do very quickly.
Absolutely.
It was number.
And thank you for asking, because you are keeping me on the right track.
It was number 35. Unfortunately, I don't have the.
That's fine. That's fine. You said in 4.9?
Yes.
Very good.
Yeah.
Excellent question. We are starting with 35 on page 349. Is that correct?
Yes.
Let me write it.
Yes.
So we have f prime of t equals 2 cosine t plus secant squared. Is this the one?
That is it.
And negative pi over 2, pi over 2. So that's the first and the fourth quadrants. And we are given that f of pi over 3 is 4. And the question is asking us, find the f. And if you notice, so see, now here the function is given at SF, and we're asked to find uppercase f. Here the function is given all the way as f prime or f double prime or f triple prime, and we're asked to find lowercase f. So please keep that in mind, the notation matters. Okay, next. We're given the first derivative, and we are asked to find f of t. So I'm asking myself this. What function prime will be 2 cosine t? And the answer is 2 sine t plus. Which function prime is secant squared? Tangent. And this is not enough. It's good, but it's not enough. Very good. Plus c. So far, so good? Okay. So now I'm told that f of pi over 3 is 4. Why is this condition given to us? The condition is given to us for one purpose only. And that purpose is to find c. Very good. So I would plug in pi over 3, 2 sine pi over 3 plus tangent pi over 3 plus a constant c equals 4. That's how we use the point. When x is, or t in this case, t is pi over 3, the function value is 4. Are we in agreement with this? Okay, very good. So now remember, in pre-calculus class, I always show my students or ask my students to remember just 3 numbers. So for pi over 6, for pi over 4, and for pi over 3, for 3 different angles, to determine sine and cosine. Why? Because it's not difficult. Always start with 1/2 for the smallest angle, and then 1/2 here. And continue with the square root of 3 over 2 here, and copy it here. And this is the easiest angle to work with because both are the same. The square root of 2 over 2 over 2. The square root of 2 over 2. So I always tell my students, and I'm telling you, don't memorize anything beyond this. There is no need. Because sine pi over 3 is this. So you have 2 multiplied by the square root of 3 over 2, and you will simplify the 2, plus tangent pi over 3 will be sine over cosine. And when you divide these two, you get the square root of 3, plus a constant c equals 4. So you have the square root of 3 plus the square root of 3, which is 2 the square root of 3. So you get 4 minus 2 the square root of 3, which is the constant. And finally, you can determine or write the entire function. F of t equals 2 sine t plus tangent t plus 4 minus 2 the square root of 3, which is the only function that satisfies the given conditions. Has that first derivative and fulfills the condition that f of pi over 3 is 4. Is this clear? Tony, is this okay?
Yep.
Okay. Anything else? Other questions from 4.9, 5.1? Yes. Page or section? Is it the same section?
Yes.
Yes, of course. It was 49? 47, I'm sorry. I looked at 49. 47. The second derivative is x to negative 2. We are told x is not 0, obviously, because this will be 1 over x squared, correct? And we are given that f of 1 is 0. We are given that f of 2 is 0. Perfect. We can jump from the second derivative to the function. We have to go through the first derivative. So by the power rule, I have to write x to negative 2 plus 1 over negative 2 plus 1. Plus a constant c. I'm going to call it c1. You can call it a, you can call it b, use any letter. We normally use c, but it doesn't matter. Good. So then this is x to negative 2, this is negative 1, and this is negative 1, correct? So it's negative 1 over x plus a constant c1. Are you okay so far? Okay, now, I can determine c1. I don't have any information about f prime. So I have to leave it as is, and I have to continue. It's a very good question. Thank you for asking that. Now I'm ready to find f of x. And I'm asking myself, which function prime is 1 over x? And the answer is, say it again. Very good. So it's negative natural log of the absolute value of x. Plus, which function prime is c1? c1x. Plus c2. Ready? Now we will be using the first condition. F of 1 is 0. Negative natural log 1 plus c1 times 1 plus c2 equals 0. How much is natural log 1? 0. So then I have the first equation that I cannot solve because it has two variables. However, I have a second condition. I am told f of 2 is 0. Negative natural log 2 plus 2 c1 plus c2 equals 0. So here's my second equation. 2c1 plus c2 equals natural log 2. I have two conditions. It's a system of two linear equations, and I will use elimination or substitution. It doesn't matter. I am for now going to copy the system on the next page. So I have c, and I'm going to multiply the first equation both sides by negative 1. Negative c1, negative c2 equals 0. 2c1 plus c2 equals natural log 2. This is my system. I'm using elimination. These two go away when I add. This is c1, which will be natural log 2. If c1 is natural log 2, c2 is the opposite of c1. Okay, when I move c1 to the other side, c2 is the opposite of c1. Therefore, c2 is negative natural log 2. Are you with me? Everything okay so far? So now I have the final answer, where f of x equals negative natural log the absolute value of x plus x times natural log 2 minus natural log 2. And this is the only function whose second derivative is x to negative 2, and f of 1 and f of 2 are equal to 0. There is no other function that fulfills these three conditions. because we determine C1 and C2 based on the given conditions. Very good question. Thank you. Are the steps clear? Any questions on this problem? Thank you for working on this. Anything else? Anything else? Okay, ready for 5.2. Is there anything else, or we continue with 5.2? Let me see the time. Okay, just 30 minutes, that's fine. Perfect. Anything else? Okay. Before I define this, we already did last time. But before we go into details and read the definition, I would like to come back to the problem that we worked on 3 minutes ago. Because this is it's fresh, still fresh in our memory. And the interval was 0, 2, correct? And we were using such and such intervals. 4, 6, no, 4, 8, 16, 100, right? Okay. Here's what I want to do. Now you imagine the graph. I'm not going to graph it again. I really don't need it. But let me go back to the graph. This is the graph between 0 and 2. No matter how many subintervals we use, this is the graph of the function, correct? If we use the leftmost point, midpoint, or the rightmost point, it doesn't matter. Because now we're going to go to infinity. So it's not going to make any difference. Okay, so I'm going to divide this interval between 0, huge, huge, and make it as big as possible so we can talk about it. It's big, right? You can say it's not really true, but I need to discuss this. So this is the initial value, x0. We heard this before, right? And this is the last one, which is xn. We're going to divide this interval into n subintervals. N. So the first subinterval I have to explain, I have to write that down, of equal length, or if you want width, better, which is delta x, and it's b minus a over n, which is 2 minus 0 over n, or 2 over n. Are we in agreement so far? And you can say you haven't shown anything, and I will have to agree. I haven't. I only said that this is the interval 0 to 2. I only called 0 as the initial value, and I only called 2 as the last value, or the upper limit of this interval. And I only said to you that I will divide this into n subintervals, and each subinterval has the same width of 2 minus 0 over n. Okay, so here's my first subinterval. This is the first subinterval, and it has the width of delta x. This is the second subinterval, and it has the width of delta x. This is the third, and now I'm sure you're going to ask, are you going to do this all the way? No. I'm going to say I will continue here, where I have xi minus 1. Then the next one is xi. What is the next one? X, of course. And then I will continue, where I will say this is xn minus 2. This is xn minus 1, this point here, and this is xn. And I'm going to say again that I created n subintervals of the same width. Now I would like you to tell me, stay with me please, once we understand this then the rest will be easier. Can you please tell me how much is x1? Can you express x1 for me?
Okay.
0 plus delta x. Excellent. Awesome. Please express x2 for me. Right. Excellent. Please express x3 for me. We always start from the very beginning. Now I would like you to jump ahead 3 dots, and I want you to tell me how much is xi. Excellent. I want to jump now to the last one. Excellent. Perfect. So now imagine I have the function up here, right? This is just the x-axis, right? So the function is somewhere up here. And it does not matter because we have n subintervals. It doesn't matter if I use the height on the leftmost point or the rightmost point or the midpoint. But the height for x1 will be f of x1 star, because it can be here, it can be in the middle, or it can be here. For the next subinterval, then I will have f of x2 star. 2 because it's the second subinterval, and star because I don't know, we haven't decided, and it's not important, if it's going to be at the leftmost point of the interval, the midpoint, or the rightmost point. So I continue in this way. That's the height, right? That's the height of each subinterval. What will be here? F of xi star. And what will be here? Very good. Excellent. So now, again, I would like to determine, notice that I am not putting leftmost point, rightmost point, or midpoint. Notice that I'm not going to put the approximation symbol. I'm going to put the equal symbol. And of course, I'm going to sum from I equals 1. How many subintervals do I have? How many? Okay, let's go back. How many subintervals we have? Good. From I equals 1 through n. And how do I write that area? Times f of xi star. Very good. Delta x times f of xi star, which is the height that I'd like to choose. It doesn't matter if it's a leftmost point, midpoint, or rightmost point. But if it's the xi for each and every subinterval,
What about the n?
I will have an nth interval. So because I start at 0, between 0 and x1 is 1. Between xn minus 1 and xn is the last subinterval.
Okay, so what I'm kind of confused at is, so you have x1, x2, x3, right? Then you go down the line a little bit, then you have xi. You go down again and go.
Yes, which means I will be from the first subinterval till the nth subinterval. That's why I had to show you the one where is the generic one. But I goes from 1 through n. When I'm at 1, I'm adding this area. When I'm at 2, I'm adding this area. When I'm at 3, I'm adding this area. I have to stop somewhere because it will take forever. And I'll say, okay, when I'm at I have this area, base times height. And the last one, same thing, base times height. And this will be the sum from I equals 1 till n. That's why we had to talk about the summation notation first. I could not throw this at you directly, right? So when I is 1, I'm on the first subinterval. when I is 2 on the next one. And then I have to finish with the last one. There will still be gaps. What am I missing here? What operator should I have in here so there is for sure no gap anywhere? I need an operator. Something that we studied from almost the first day of this class. Thank you. Sn approaches infinity. Now that's the reason for this limit. The limit operator allows me to use the equal symbol. If I don't have the limit operator, it's still an approximation. But once I say n approaches infinity, there is absolutely nothing less or more than the exact area. It takes into account everything. There is no overestimation or underestimation. Once I put the limit in there, it's done.
Isn't it a limit of the approximation itself?
Nope.
Make that?
Yep. Yep. The limit of this, when n approaches infinity, will give us the exact area. Yes. Okay, so now let's fill this in. Let f of x be a continuous function. It has to be a continuous function on the interval a comma b, otherwise I can't determine the area. And if the function is not continuous, you have to wait till calc 2 to find something there. Okay, so the function must be continuous. Divide the interval in n subintervals of equal length, and this is the delta x, where a starts from so on and so forth, and b, so a is x0, as you know, x1, xi, or xn till the xn, are the endpoints of these subintervals where n has the value. So then I showed you what I just showed you a minute ago with xi. Just that oops, this is 3. The definite integral of f of x, I'm not discussing this just yet because I want to talk about the summation first and apply it because we didn't get the chance to. So forget about this sentence for the next half an hour. Okay, so the area is given by the limit from I equals 1 through n, delta x, f of x psi star, as n approaches infinity. And then we will write what it says here. But allow me to show you a couple of examples with this because we didn't get the chance to. And then I'll come back. So evaluate the Riemann sum. So we can start with this first example if you want. Evaluate the Riemann sum. We can start with this. You choose. So let's choose an example, either A or B. And you can do the other one. We want to do B. Very good. So we have the function 2 plus 3x plus 2x squared, and the interval is 1 comma 5. So we're asked to find the area of the limit of the Riemann sum. The limit, so the problem is asking us to find the Riemann sum, but then we want to find the limit. So the whole thing, the exact area. So prep. I cannot do that before I go through some preps. First prep is, what do you think? What was the first thing we determined here? Exactly, thank you. Excellent. Of course, delta x. By definition, b minus a over n. b minus a over n, which is 5 minus 1 over n, which is 4 over n. That's my first prep. Prep number 2, xi. But we know what xi equals to. The initial value, in my previous example it was 0, the initial value plus I multiplied by delta x. So I'm ready. The initial value plus I delta x. So I times 4 over n. But I would like to write it like this. But it's I times 4 over n. Prep number 3. I need f of xi. If you want xi star, same thing. Doesn't matter. Okay, so I'm looking at my function. This is my f of x. The initial value plus I times delta x. So if I write I times 4 over n or 4I over n is the same thing. Is that clear? Good. So now I want to find f of xi. Here's my f of x, and here's my xi, or xi star if you want to call them. It doesn't matter. We don't have to mess with that I. It just is with that star. Just the star is in your book, and I don't want to get you to get confused. There is no need. The xi star only says that it doesn't matter if it's the leftmost point, the rightmost point, or the midpoint. Okay, so here's my f of x, and here's my xi. What do I have to write? F of 1 plus 4I over n. Not trivial. I have 2 plus 3 times 1 plus 4I over n plus twice, in parentheses, 1 plus 4I over n squared. Do we understand this step? I just plugged in the function xi. Is that okay? Are we okay? Okay. This is not enough. I have to completely simplify this. Why? Because I'm going to have to put it here in a summation notation. Ready? So, I distribute 3 plus 12I over n plus 2 multiplied by, we know how to square binomial. How many terms will you give? We have an agreement from the beginning of this class, 3. So the first term squared plus 2 times the first times the second plus the second term squared. Are we okay so far? Two plus 3 is 5, plus 12I over n, plus 2, plus 16I over n, plus 32I squared over n squared. I removed parentheses, I squared. I'm continuing to combine like terms, and I will put the answer in descending order of powers of I. Which one is the first term in that case? 32, yes, I squared over n squared, plus these can be combined into 28I over n plus 7. I'm done with my preps. I prepared 3 things. I prepared this, and I prepared this after I determined xi. Now I'm ready to put everything in the limit of the Riemann sum. I have this, I know how to handle this, and then eventually I'll get the limit. So now I'm ready to put the pieces together. So the area equals the limit. Sn approaches infinity from the sum from I equals 1 through n. Delta x is 4 over n multiplied by f of xi, and in parentheses this whole thing. 32I squared over n squared plus 28I over n plus 7. One property that we looked at last time was this. A constant that is a factor can go outside of the summation notation. This is a constant, does not depend on I. It will go between the limit and the summation notation. So this equals limit n approaches infinity 4 over n. Now, we know this property. The sum of AI plus BI is the sum of AI plus the sum of BI. That's exactly what I'm going to do. Bracket, the sum of the first term plus the sum of the second term plus the sum of the third term. This is one of the theorems. The sum of a generic term plus another generic term is the sum of the first one plus the sum of the second. I have 3, I have to use it 3 times. From I equals 1 through n, from I equals 1 through n, and from I equals 1 through n. And I already made a mistake by not copying the power 2. Sorry about that. My next step would be, I'm coming back to this. A constant multiplied by the generic term that depends on I goes in front as a factor. So then I will continue writing limit as n approaches infinity 4 over n. So this is a constant, does not depend on I, will go in front. 32 over n squared, the sum of I squared, from I equals 1 through n, plus. This is a factor, goes out in front of the summation notation, from I equals 1 through n of I, plus. This goes in front as a factor, 7, the sum of 1 from I equals 1 through n. So I applied 2 of the rules or laws or theorems that are applicable to the summation notation. So one more time, it was the sum of a constant times generic terms, sum of generic terms, so that went in front. And then the sum of AI plus BI plus CI is the sum of the first term plus the sum of the second plus the sum of the third. I'm applying the same property again that allows me to take a constant in front. As long as it's a constant, that it's a factor. Constant is a factor in front. 7 times 1, so 7 goes in front. And now I learned something last time that will help me replace this and replace this and replace this. Don't erase it like that. I'm just making a point. So what do I replace? Let's start with the easy one. What do I replace this quantity by? This one. Very good, excellent, awesome. What do I replace this quantity by? n plus 1 divided by 2. And what do I replace this quantity by? It's n plus 1, 2n plus 1 divided by 6. Why? How do I know these? From here. The sum of I squared is n plus 1, 2n plus 1 over 6. The sum of I, n plus 1 over 2. And the sum of 1 is n. Yes? Tom?
Would you mind just going over those? I think last class we said we were going to hit them, and I don't think we did.
We are going to prove them?
Not prove them, I guess just explain them.
Oh! So this means when I is 1, I have 1. When I is 2, I have 1. When I is 3, I have 1. When I is 4, I have 1. Plus, plus, plus. 3, I have to have exactly 3 dots. 1. And this is n. Because I'm adding 1 n times. Now this one means 1 plus. When I is 1, I get 1. When I is 2, I get 2. When I is 3, I get 3. Plus dot, dot, dot. Plus when I is n, I get n. And this can be proven using mathematical induction. That is n plus 1 over 2. When you add the first n terms in natural numbers in any sequence, you will get n plus 1 over 2. For example, so let's say you want to add the sum of I from I equals 1 to 2000. You're not going to sit here and say 1 plus 2 plus 3 plus 4. You are going to say 2000 times 2001 over 2. You divide, and you get 2001000 by using this result. Or you use the calculator as the sum of the sequence. Okay, what will this be? Exactly the same, but with power 2. What will this be? Exactly the same, but with power 3. 1 cubed plus 2 cubed plus 3 cubed plus n cubed will be the same thing, but squared. So these two are very similar. And the only thing here that is different is the 2n plus 1 and the denominator, which is 6. But yes, you have to remember these. They are useful. Okay, so is this okay so far? Okay, so now we are back. I managed to get rid of the summation notation. So now I continue. Limit as n approaches infinity 4 over n. So now I have 32 over n squared. And I replace this by this. But I will already multiply these two. So then I have multiplied by n, and this is 2n squared plus 3n plus 1 over 6. I only dealt with this portion plus. Now I'm here with 28 over n multiplied by n plus 1 divided by 2, and finally plus 7n. Are you okay with this so far? Okay. So what did I accomplish? A lot. I got rid of this. These were in the way. But I managed to replace them by what they are equal to. Okay, now I'm looking at this denominator and this denominator, and I realized that I could simplify an n, and the denominator here is 2. I cannot reduce this to 2, so the denominator will still be 6n. So I have the limit as n approaches infinity from 4 over n. Obviously, the least common denominator will be 6n. Here, all I have to do is just distribute. So I have 64n squared plus 96n plus 32 plus, here I have the denominator of 2n, but it's 6n, so I have to multiply it by 3. So I have, what do I have here? 4, right? And 8. Okay. N squared plus 84n. And finally, I multiply 7n by 6n. And I get plus 42n squared. So now from a sum of 3 fractions, I have 1 fraction. And let's see what else I can do here. So this is limit n approaches infinity. I'm going to simplify by 2. Now the denominator becomes 3n squared. Now these have n squared. So 42 with 64 is 106. 106 with 84, I think, is 190. And 190 multiplied by 2. 380 n squared. Now I'm going to calculate these. And I'm going to say, I refuse to calculate it. Well, you can, of course we will. But I don't need it. N plus 64. Now I would like someone to tell me this limit. When n approaches infinity, the top approaches right? The bottom approaches right. So what do I use? L'Hopital's rule. However, when the degree of the top and the degree of the bottom are the same and the limit goes to infinity, the answer is, okay, we don't remember, let's use L'Hopital's rule then. So limit Sn approaches infinity, I use L'Hopital's rule for the top. 2 times 380, that's 760n, plus whatever number is that, delta, over 6n. I just didn't calculate delta, I don't need it. Now where does the top go? Where does the denominator go? What do I use? Right, and the answer is? That's all I wanted you to say. Same degree over same degree is the leading coefficient over the leading coefficient. So I simplify by 2, and I get 380. So the answer, the exact area, no questions asked, the exact, absolute exact area under the graph of the function we picked between 1 and 5 is 380 over 3. A lot of work with the limit of the Riemann sum. Yes. But now I would like to go back to my handout. There is a second way of determining this. Now notice one thing. If the function has sine in it, or cosine, or tangent, I cannot find the limit of the Riemann sum. I'm restricted to these 3 options, 4 options if you want. I can only determine up until including degree 3. I cannot determine the limit of the Riemann sum if it's anything else other than a polynomial, degree 1, 2, or 3. I don't have anything else. I'm restricted, limited to these 3. Okay, 4. So, no one can ask you to find the limit of the Riemann sum on anything else but a polynomial up until including degree 3, period. Okay, so what do we do otherwise? What do we do the rest of the functions? Because there are tons of functions. Okay, let me stop.